Imagine this. One of your university's research groups has just won a lucrative new research project. It requires pulling together a cross-department group of 20 people. They need to be provided with wet lab accommodation, write-up space, and engineering workshops. Some of the equipment that will be needed weighs several tons and is to be brought in from elsewhere. The research project requires dedicated high-capacity service supplies. This requirement will not fit into one of your regular laboratories. There isn't time to design, build and fit out a new purpose-made laboratory, so in this situation, what could you do? If this could happen to you, one solution to consider is to decouple the design of the building's shell, the walls, the floors and the roof, from the design of the internal fit-out. In other words, to build a bare shell and then, at a later date, to fit it out. This proposal is essentially a refurbishment or retrofit project, but without the first-time users. So, without a first-time user, what's the brief for the shell? Or, more helpfully, what are the characteristics of a building that is ideal for retrofitting for research projects? The answer to that question becomes the brief for the shell. This type of building is known as an open or adaptable building. Oxford University has built 2 of them at Begbroke Science Park. 5 miles northwest of the city centre, close to the airport, is Oxford University's Begbroke Science Park. A 15th century farmhouse provides some of the common facilities for the new science buildings which are grouped around. These buildings provide flexible accommodation for research groups working on a wide variety of projects. This building is going to be adapted many times throughout its life to accommodate new research programs, so flexibility is paramount. Research programs may be desk-based or laboratory-based in either wet or dry laboratories. They may even include engineering workshops. With so many potential occupiers, we recognise this as a brief for an open or adaptable building. Much of what makes this building's design special will be hidden from view once it's fitted out, so we timed this visit in the brief period between the completion of the shell and the commencement of the final fit-out. The best place to start is up on the roof. So here we are out on the roof of the building. Below us there's the potential for 2 floors of laboratories, and that means that for every square metre of laboratory space there's about half a square metre of plant room space up here. That's just about the ideal ratio. We anticipate this plant area could be used for heating, ventilation or cooling plant, but it'll also be used in association with the research that's going on downstairs. So there might be fume-covered discharges, there might be arrays of photovoltaic panels. If you look across to the south wing is in full use, 2 floors of laboratories below that. And you can see that the roof is intensively used with plant. We always knew that this was going to be a very popular area for putting equipment, which is why we made sure that the access was very safe and easy, and we made sure that there was a safe parapet all the way around the edge. So how's the roof made? Well, it's a concrete roof that's supported on the steel framework below. On top of the concrete, there's a waterproof membrane. On top of that, a thick layer of insulation, which is then protected by the pebbles and by the paving slabs that I'm standing on. Small pieces of equipment up here could be placed on top of the paving slabs, just like these cable trays are around the edge. Larger pieces of equipment could be carried on galvanized steel frames, and these would be placed on top of the concrete pads that we can see here. These pads go down through the roof and are supported on the steel framework below. It's really important that there's no fixings going down through the waterproofing, because the equipment below is very expensive and we want to make sure there's no risk of any water ingress at all. So how do you connect the services to the plant that we're going to put up on this roof? All the way around the perimeter there's a high, wide parapet, and this provides complete safety to anybody who's working out on this roof. But it also gives us the opportunity to bring up services from below, turn them through 90 degrees and bring them out through this vertical face. And this is straightforward industrial cladding that's very easy to cut holes in And it's very easy to repair again afterwards when the experiments are finished and the equipment's been taken away. We call this feature the periscope. It's where the surfaces rise up and they come through the vertical face and appear. Let's go and have a look inside the building now. So here we are on the first floor. Let me show you what we were looking at when we were up on the roof. Above our heads here are the precast concrete planks. On top of the precast concrete planks was the waterproofing, then the insulation, then the paving slabs, and that's where we were standing. And across here, this is the periscope feature. And if you look up, you can see the white painted industrial cladding, and you might just be able to see the white painted industrial cladding on the vertical face. Air ducts rising off equipment up on the first floor here would go to the soffit, come across the soffit, and then turn and turn again and exit through the vertical face of the cladding. In similar way, experiments that are taking place on the ground floor can have ventilation ducts that come across under the concrete floor and rise up through holes at the perimeter, up into the periscope and ventilate out. You can also see running along in the periscope is the cable tray. And what we can do is bring in additional power supplies or gases through the vertical riser at the end of the building and bring them along the length of the periscope and in to suit any experiments that are taking place on this floor. The precast concrete planks forming the roof are carried on a steel frame. The steel frame is on an economical 7.5 by 7.5 metre grid. You can see that there's a tie beam running in this direction that is concealed. It's encased in concrete. It's like that so that any services running across the soffit on their way to the periscope don't need to downstand below the beam, but they can go straight the way across. The soffit to floor height is about 3.7 metres, and that's large enough for fume cupboards or any large piece of equipment that we might want to put on this floor. The building can be naturally ventilated. It has opening windows at low level and opening windows at high level. The concrete soffits can be left exposed to assist with natural cooling in the summer. Let's go downstairs and look at the ground floor. There's another example here of how this building can cope with change. Above our heads we can see there are narrow concrete planks, and immediately up here there's one that's been partly removed. If necessary, all of these planks could be removed, and that can be achieved without the need for any specialist trimming steel. Let me tell you how we've managed to do that. You can also see there's another steel beam which is set within the depth of the floor. This enables short planks to span between it and the edge of the building, enabling them to be removed very easily from above. When they're removed, they can accommodate services that run across the soffit, turn through 90 degrees, rise through the first floor, and then leave the building through the periscope above.
In the elevations, this economical, flexible approach to design has been maintained. Composite panels are supported by an internal framework of cold rolled steel sections. These can be lined as part of the fit-out. You can see that the heights of the composite panels vary. To avoid wastage, we carefully selected the most economical panel dimensions available.
This is a very special building. It recognises that change will happen. By decoupling the design of the shell from the design of the fit-out, we can deliver research space in less time, perhaps saving a full 12 months.
Not only is the initial fit-out quicker, but thanks to the open, adaptable design, economies can be delivered throughout the life of the building, as each succeeding retrofit project is undertaken.